Before we get started talking about quality assurance project plans, let me just say that the easiest way to write one is a little bit at a time. And don't think of it as this big giant burden that you have to do while you can't do all the other work you're supposed to do. Use it to help you with your project. Start with element 7, which is objective. Why are we making these measurements? And write it down, the answer to that, in a sentence or two. And that suffices for the first part of element 7. While you're thinking about this and jotting down some things, email people. Say, these are the objectives that I'm proposing for this project. Establish baseline concentrations. Might be the only objective you have. Ask other people involved in the project to review each section, and each section might be literally one sentence. It's boring. I'm really sorry. There's just no way around it. You don't want to be like this person burning up $100. And really, we're talking about a lot of money that's wasted because people get too excited, they start monitoring. And what's really tragic is a lot of times, maybe they were doing everything fine. Maybe they did have their instruments calibrated, but their data isn't legally defensible because they didn't have a quality assurance project plan. They didn't have all this stuff documented ahead of time, and the data really can't count for that much at that point. So if you start writing your quality assurance project plan as early as possible in the process, it'll document your process of planning, any agreements that you have with any outside entities like laboratories or other consortia. The people who are part of the project have to sign it, which is really useful because most people don't like signing things that they haven't read. It documents who does what, when, how, with what equipment, and who's supposed to report what to whom. It helps eliminate later misunderstandings about what somebody was supposed to do. It's helpful because everything is contained in one document, at least if you include the attachments like procedures. And then it is a public document in case of disagreements. There haven't been any cases that I know of involving tribal quality assurance project plans, but basically, anytime data is contested in court, the first thing that the judge will ask for is the quality assurance project plan, not because they're familiar with the term, but because they look it up and say, oh, okay, that's the first thing people are supposed to do. Okay, let me see it. Just start with one of the examples we've got in the course website. People have really generously provided copies of quality assurance project plans. I have an example template QAPP for a Category 4 project. So look at other people's examples and just do one section at a time. EPA has a graded approach for quality assurance project plans, which is great because if everybody had to write a full-blown QAPP, those are really meant for people who are monitoring to determine if their area meets the federal air quality standards or not. And that's huge. You have to use specific kinds of instruments. Not everybody, and especially people starting out, have to have a QAPP that's so detailed. So those people have a Category 1 project who they want to compare against the federal national ambient air quality standards, and they have to have a full-blown QAPP. And a lot of times those are hundreds of pages long, not even counting the attachments. The middle category are those that are looking at other things, exploratory studies, or evaluating whether further measurements should be made. And then down the scale to talk about more local decisions where data is being gathered, but it impacts a local area rather than like the federal standards. These include education and outreach projects, and these require a smaller quality assurance project plan, only 6 elements plus the signature page. And we have an example of a Category 4 QAPP in the course downloads folder. And then this is a link to the EPA's policy for a graded approach, where they provide more examples of these different kinds of QAPPs. So we're going to go through a QAPP now. I'm going to review in general the category 4, so talking about the 6 elements plus the signature page. Before you get out there and get your hands dirty in the mud, before you send a team of volunteers, I've worked in projects where we've had volunteers from the school, we've had volunteers from local community college. Before you get all your people together and you send them out there doing work, make sure that you've got your QAPP developed and, if possible, approved, so that these people's time isn't wasted. First of all, the title page is fairly simple. The important thing to recognize here is that you need to make sure that the people who sign the QAPP are those people who are going to be doing the work and people who are providing any funding, as well as any other oversight people other than getting their signatures. Sometimes this is probably one of the easiest elements of a quality assurance project plan. What you need for a category 4 project are these other elements in addition to the signature page. So you need a project description. You need to talk about the objectives, and we've been talking about that. What information are you trying to gather? What's the object of this? What's your question? Is the dust higher than a standard? Is the dust maybe higher on one road than another? You could be asking those sorts of questions. And then the criteria for your data. And that generally you get from the equipment manual. Most owner's manuals have a page that's a spec sheet where they give you the criteria that they have as a manufacturer of your equipment, where they say this is how well this piece of equipment works. Then the next element of a category 4 QAPP is the project design, and that really is just mostly siting of the monitors, where the monitors are going to be, how often they're going to measure, or like if this is a summer only project or a winter only project. Some things like how far up off the ground the equipment has to be, things like that in the design, the sampling design. And then the next section is analytical method requirements. And this is just how your equipment works. If you're using a lab, if you're gathering samples and sending them to a lab, then you're going to be pulling out the requirements here from what the lab sends you in terms of if they're using a standard method, and then what their limits on their QC is. And you're basically just going to trust the laboratory, but you have to get the information from them because you want to know what it is that they're doing so that your money isn't wasted. And then you include it in your QAPP so the people who have to sign it say, oh, okay, she's done the research. This sounds like a good lab. They're doing the measurements of the samples the same way, according to the same standard EPA method that the lab that I used did. And so therefore, our results could be comparable. So that's what analytical method requirements is, the requirements of your method or the analyzer, if you've got a handheld analyzer or piece of equipment that you've got that you read numbers from. Then QC requirements. This doesn't have to be long, but it just has to basically say stuff like, I'm going to do a startup check every time I go out and I restart the equipment. I'm going to log it. I'm going to check the flow rate, and the flow rate has to be within these limits, between 4 and 6 liters per minute. And if it isn't, then I have to do some checking on my equipment. If I can't troubleshoot it and fix it myself, it has to be sent back for recalibration. So again, these sections don't have to be long. Then the last section, data management, is how are you going to get data off of your equipment or from the laboratory, and what are you going to do with it? You're going to put it into an Excel sheet. You're going to calculate averages. It doesn't have to be really specific. It just has to show that you've thought about this ahead of time. And then, of course, you're going to have appendices. The owner's manual of your equipment is good to have, especially in electronic form, because then you can cut and paste from it. If you've got any procedures that you have developed or that you've copied from the generous people who are on this call. And then references. Make sure that if you cite any references, you should have them. So find them on the internet and read them, because you don't want to be embarrassed by citing a reference and then turns out you just copied that QAPP from somebody and you really have no idea what that reference is. So again, take ownership of this. Make sure that you do your research and don't include things that don't make sense to you. Just because somebody else had it in their QAPP, it could be that they shouldn't have had it in their QAPP and it didn't make sense to them. So make sure that everything you have makes sense to you and is useful to you, or else don't include it. So the next element is the project description. And this is fairly straightforward, where you say, first of all, are you comparing against a standard? So even if you cannot say, I am in compliance with the National Ambient Air Quality Standards or not, using this dust track data, because it's not the kind of device that could be used for that purpose, I'm still making measurements of particulate matter. I still could compare against it for my own purposes. If you're making measurements to establish a baseline concentration, just state that this is the description of our project. We're gathering data to establish baseline concentrations of particulate matter of 10 microns or less along these roads in our community in the winter months. Whatever it is, the description of what your goal is goes in this section. And this is just the standards for PM10, 150 micrograms in 1 cubic meter over 24 hours is the federal standard for PM10. And for PM 2.5, so that's particles 2.5 microns in diameter or smaller, and these are the more dangerous particles that get deeper inside our lung, and it's harder for us to cough out. That standard EPA has just lowered to 12 micrograms per cubic meter as an average over a year. So these are some of the standards, and I've got a list of the federal standards in the course downloads site. Here we have a picture of Tracy and Michael in front of their truck with the equipment that they have to take around. And this organization pertains, in the case of the Seldovia village, to these people. What are they doing? Who's responsible for what? How often will Tracy go out into the field? How often will she check the flow rate of the dust track? How will each person do their job? Well, there's an SOP that's attached. To whom will they report? Do they report to ANTHC? Is there another mid-level supervisor they have to report to? So again, this doesn't have to be long. It can literally, especially with small programs, be just a few sentences long. The project background is important only because, especially for the funding agency, it's important to know why it is that you have this question. Have there been more complaints of dust? Has there been more complaints of asthma? Asthma rates are skyrocketing. You want to provide context. For example, if you want to establish baseline concentrations for future work, that is an appropriate background to provide, especially because this is a picture of the mountains by my house. You can see a good visibility day and a bad visibility day, and I'm very curious about what causes the increased dust in the air. Or is it dust? And your QAPP should assume, to some extent, an ignorant reader. So a member of the public, if they picked this up, would they say, oh, wow, I understand why they want to do this project. I'm curious about these things also. It's also important, really important, and especially to your funding organization, that you research existing information. So if there's any information that's out there from earlier studies, chances are not in your particular location, but maybe another place that's similar to you, whether you're on the coast or inland, where they've done similar studies. Maybe even if you didn't gather the data from these other studies, you could find it useful to you when planning out, are you going to monitor during all months of the year? What problems did they encounter in cold temperatures? Emissions inventories, those are projects in which you basically make a list of all the different types of facilities and sources includes roads, it includes agricultural fields that can be sources of air pollution. If there are emissions inventories that have been written that include your area, results from compliance monitoring of nearby facilities. So if you've got facilities where they have done some air monitoring, can you get those results? You'd be really surprised what you can find on the internet if you spend some time. Field work, that's another important component. You have to describe what kinds of measurements are being made, what kinds of samplers, how many measurements you plan to gather over what time period, and locations. Here's a picture of somebody doing water sampling, and here's a picture of Tracy, and you can see that they had to modify their monitoring and include a camouflage box for their monitoring, and that's another thing in terms of lessons learned, where there's obviously something that they learned that might be useful for you. If you're using a laboratory to analyze samples, just state the method. If you are using a laboratory that's using an EPA standard method, reference in your QAPP the standard method IO 14 or whatever it is, the name of the laboratory. Try to get as much information as you can from them. You should be able to obtain a copy of the laboratory's quality assurance project plan. Talk to me if you can't. But as a client paying them money, they should at least get you their quality control limits and their quality control results. But in your QAPP, you just have to state the standard method that they've used, and if possible, whatever quality control measures they've got for your kind of analysis. Schedule. This section on schedule can just be one sentence saying, we will conduct this project in accordance with the schedule shown in Table 1, and have a table where you have the activity. First, we're going to get the sampler and we're going to test it. Then we're going to start testing December 1. Sections don't have to be long, but you have to really think through all your different milestones. Data quality objectives. This section you have already begun because it starts with, what am I monitoring for? Why am I doing this? What question do I have? And the idea behind this section is that it's supposed to get you where you want to be so that your data are good enough to answer your question. Now, your data don't have to be as good as possible. You know, you can measure things down to such a fine and detailed level, and that could cost a lot of money. You just need data that's good enough to answer your questions, and no better. These items in red are called data quality indicators, and we'll go over each one of these. First, accuracy. Accuracy is total error, and that's measured by doing an audit or a comparison where somebody ideally would come to Tracy's device and set down their own dust track and make measurements side by side and compare them. And that way they would be comparing their whole system against Tracy's whole system. In general, we can't pay for auditors to come and do that, but you've got things that you can do to try to minimize your total error and estimate it. Precision is the wiggle. Now, if we were doing this class in the classroom, I would now do my precision and bias dance, in which the precision is the wiggle. So your instrument is never going to operate totally perfectly. It's going to wiggle around a little bit, sometimes high, sometimes low, sometimes high, sometimes low. It wiggles around the truth. The bias, on the other hand, is a consistent jump, either high or low. If you've got a bias error, that means your instrument is consistently reading either high or low. And again, sorry, I cannot do the precision and bias dance. Representativeness is whether what you're measuring really represents the population that you are after. So think in terms mostly of location, where you're making your measurements. Is that really representative of what people are breathing or what I'm concerned with? Or maybe you're interested in air pollution from a particular source. In that case, you want to be downwind of the source. Times of day, times of year can be really important for representativeness. Then comparability. Can you compare your results with somebody else's? And comparability comes down to a lot of things. Most importantly, your choice of equipment. It doesn't have to be the exact same equipment, but they should be measuring the same thing. Dust in the same particle size range, for example. And then following the same procedures in terms of distance from a road, times of year, etc. Because it's really important that you be able to compare against other people and what they found. And even in the future, if you're conducting a baseline study and you want to compare again in 2 or 3 years, obviously you want to make sure that you're measuring the same thing so that you compare the results. Then detection limit. How low can your device measure? And that's something that's just built into the type of device and its design, is the detection limit. But not so much for particulate matter, but for volatile organic compounds, for example. Sometimes we can even smell things like hydrogen sulfide, smells like rotten eggs, and people can smell that at super low concentrations. Do the devices even measure them at low concentrations where people can smell? Is that relevant? Completeness. How many values did you gather? We all strive for 100% completeness. In general, the goal is at least 75% completeness. If you're doing an indoor air quality study and you are going house to house and building to building and you're doing a survey, well, you know you're not going to have all the questions answered. You're not going to get responses from people. So the completeness is important because you want to try to get as complete as possible because you're using your subset of people who answer those questions and you're extrapolating it to the whole population of all the buildings or all the homes. And you're saying this is representative. That's why we want completeness to be as high as possible. And you want to measure it so that you'll know, was my completeness 15% or was it 90%? That can make a big difference in how you can interpret your results. Accuracy is total error. And total error means the difference between your result and the truth. Nobody can measure the truth exactly. So we've got in Seldovia Village, there are these roads and there's dust kicked up. Tracy cannot go and take her dust track and monitor every single little particle of dust, every little bit over all this road. She has to pick one place where she makes her measurements, and she tries to make it so that it's really representative of the air above the roads in general. But there's going to be some difference. Because we can never measure the truth perfectly, we're trying to just estimate it with our devices and our measurements. If you think about it, realize that the total error is composed both of bias and precision. In terms of bias, it may be that the dust track isn't placed on the most representative bit of the road, and it could be that there's a bias where really some of the road has dust that's higher than where she's monitoring for it. It may be that the dust track bounces around a lot in terms of its flow rate. So the total error is composed of both of those different things. And the best way to estimate total error is when an auditor comes and sets up their device side by side with yours. But most times we can't afford this. So we try to minimize this total error by following the same procedures every time. Because you could see that if sometimes you came and you operated your instrument one way, and sometimes you came and you operated it a different way, even if it wasn't obvious that it was doing something different, maybe you hold it up to see the light and then the angle of the sun means that you always don't see the last digit or something like that. But you only do that when you're there in the afternoon when the sun is in your eyes that direction. So sometimes you've got more digits than others. Well, that could maybe over time create a difference in your overall average. So it's really important to try to do the same thing every time, and that you're strict about when you take your measurements and where you take your measurements. Because we know we're never going to be 100% accurate, we estimate our errors by making quality control. It's just a way that we can try to estimate how far off from the truth we are. Precision error. This is the wiggle. So sometimes high, sometimes low. In our thermometer example, does it read the same every time? How much does it vary? If you take it out of your mouth, turn it on and off, on again, and then put it back in your mouth, does it say the same thing, even if you know you didn't suddenly get a fever? It might vary a little bit. Sometimes people call this readability. It may vary by 0.1 degrees Fahrenheit. Well, you know that doesn't make that much of a difference when you're trying to decide whether to send your kid to school. If their fever is over 100, they shouldn't go to school, whether it's 100 or 100.1. But you could see that if you charted your kid's temperature over months and it varied, it would wiggle around. This is an estimate of the precision error in the thermometer. It's not that great of a thermometer. It costs $6 at Walgreens. So it's going to wiggle around a little bit just based upon whatever minimal electronics it's got in it. If you've got a mercury thermometer, those things are hard to read, and that's when readability comes in. You hold it at a slightly different angle, it could read quite a bit off. And that also is part of the precision error, because that's how you're using the equipment. Precision is the wiggle in the result, sometimes high, sometimes low, but how much? You can never eliminate precision totally. Your job is to keep it within the bounds, and in general, that should be specified in the owner's manual, and track it so that you know what your precision error is, or at least you have some estimate of it. And this is a link on the course website, videos of precision and bias about thermometers in ice water baths, because everybody who makes environmental measurements has to take temperature readings. So this is a link to videos on precision and bias. So let's look at the numbers we're talking about with precision. We're going to go over this again in more detail with different numbers, but I just wanted to introduce this topic in terms of flow rate. These are dates in this column, and these are quality control measurements of a mini ball, which is a very, very simple air monitor that pulls air through a filter, and the target flow rate is 5 liters per minute. And you can see that before I started my measurement every day, I measured the flow rate, and it's not the same every time. Sometimes it's right on what it's supposed to be. Sometimes it's 6. It got down as low as 3, which is too low. It bounces up and down, but in general, it's around this red line, which is 5 liters per minute. So what this chart shows is on the x-axis every day, we've got the value plotted. So the first day is on the 2nd of March, and that's 5 liters per minute. And then the next day I went out and I made another measurement, and then it was 6 liters per minute flow rate. But you can see that it goes up and down a little bit, not too bad, although this number is low. And this is an estimate of precision. I cannot get this mini ball to operate any more precisely than this. And this is the way these mini balls go. You can't even really measure because it's got a little rotometer, so it's really hard to even see what the flow rate is exactly. But this is how you would estimate your precision using quality control measurements of the flow rate. This again is wiggle. So you're wiggling around, sometimes high, sometimes low. And really this is as good as we can get, and we're satisfied because this is within the limits of the instrument, and we are estimating our precision error. Bias. In our thermometer example, What happens if we put it in our mouth versus putting it in our armpit? The difference of 1 degree in general is bias between the two locations. This is one example of bias where you're talking about the sampling location. Bias, remember, is the jump. So consistently high or consistently low. In terms of the Seldovia Village road dust project, if the monitor was placed at a location that got a lot more traffic than another location, it would produce numbers that are a lot higher, and that might be a bias high because that high location might not be really representative of the whole extent of the road. This is an example. If people wanted to estimate the height of Americans, and for some strange reason they just had a sample of basketball players, they would obviously estimate the height of Americans to be like 3 feet taller than what the average height of Americans really is. And that's why it's important to really think about where you're making your measurements. What's the sample of air that you're sampling? And is that really representative of the whole population? The bias is the jump in the result between what your device says and what the truth is. In the case of the body temperature, your true body temperature. Instrument bias, and that's the bias, like if you've got say a dust track and it's monitoring dust in the air, but its flow rate is high, it's going to say you have a lot higher concentration because its flow rate is actually high. If you've got a high flow rate, you need to recalibrate it because you're going to be consistently high. Again, bias is whenever you're either consistently high or consistently low. And that's why it's really important to track whatever you can of your instrument ongoing so you can catch it as soon as possible. Because if something happens, you have a lightning strike, or you have to change the batteries and then you don't do another QC measurement, your, for example, flow rate could change. You could have a bias and not know it. And then when you find out that you have a high bias, you probably need to invalidate your data back to the last passing QC check. So the more QC checks you do, the less data you might have to invalidate if one of them fails. For a lot of air monitoring, flow rate is the most important parameter. So if the flow rate is too high, your results are going to be biased high. If the flow rate's too low, your results are going to be too low. This is another mini ball, a second mini ball, that had some problems. The precision it actually seems to be bouncing around less than the other one, right? It's not bouncing around so much up and down, but it's consistently high. What this means is that I have a calibration problem and I need to recalibrate the flow rate so that I bring this line down, and then I'll still have this wiggling imprecision error up and down, but at least it should be up and down around this red line, which is the target flow rate of 5 liters per minute. I probably, around this point here, should say, this is consistently high. I need to get this instrument recalibrated. Representativeness. You want your instrument to measure the same thing that you want to compare to. Taking a look at this picture here, you can see that there's a plume of pollutant coming from this facility here. If you're trying to sample what in general the water quality is like, you probably don't want to measure in this plume. But if you want to measure what this facility is emitting, you want to measure in this plume. Location is really critical to making sure your data are representative of what you want the data to answer. So in the case of the Seldovia Village project, you could see that they placed their analyzer not right next to the road, because there's problems that you encounter with sudden giant bursts of dust every time a truck goes by, but you don't want to be so far away from the road that you're not measuring anything that comes up off of the road surface. You also want to think about height up off the ground. Location is really key to representativeness. In this case here, we have some fires and then air monitors. And these air monitors are actually trying to monitor what is in this smoke, which is a good thing, because if they were trying to monitor just general air quality in the forest, they would do a terrible job at that. Make your data representative by picking a good site, appropriate times of year, and appropriate times of day. That can be really critical, especially in terms of road traffic patterns. Comparability. How well your data set can be compared to somebody else's, even if you're talking about in the future. So if you're making measurements for baseline data, you're going to probably want to make measurements, or somebody else will in the future. You want to make sure that your data are completely defensible. You document everything, and you're using equipment that measures what you want. So the right particle size, for example. If you are measuring to compare against the National Ambient Air Quality Standards, you have to use either an FRM, which is a federal reference method, or FEM, federal equivalent method, and follow procedures exactly. And the reason is that EPA wants everybody in the whole country that makes measurements with these pieces of equipment and they compare against the standard to have data that just can be piled all together into one giant data set. And that's basically what they do, because they're so strict with everybody following the same procedures, so that if you make a measurement using an FRM in Alaska and somebody else makes a measurement using an FRM in Alabama, you can compare those two data sets, and you know that you're comparing data that was gathered the exact same way. In most cases, you're not monitoring to compare against the National Ambient Air Quality Standards, but you want to, as much as possible, use methods that other people have used, and you want to follow similar procedures. The Seldovia Village folks have generously provided examples of their SOPs, and I've got some other SOP examples in the course downloads folder. Careful citing and schedule is really important for comparability. If one project is conducted in the winter and another project is conducted in the summer, it may be that there's not that much you can compare between the two, because they're really measuring different things. Detectability is how low can this be reliably measured with this piece of equipment. This is usually in your instrumentation manual, and generally you can find those online from the manufacturer's website or in the laboratory QA plan. Get a copy of that if possible, or at least of the standard method, and they should have a table that includes the method detection limit, and then completeness. How many values did you gather compared to how many you meant to gather? And that's just a percentage. Completeness is impossible to get to 100%, but it's important to try to get as much as you can in order to make sure that your data are as defensible as possible. That is it for this first webinar. For the completion certificate, please go to this website and download the homework and email it to me. And thanks to all the partners who've been really generous in providing their examples and material for these webinars for all of you guys.